Hi all. So I'm recording this video to explain you a project which I have been developing for the last 6 months. So I have developed architecture which is a hierarchical transformer architecture, which kind of accepts morphologically rich languages and kind of does sequence modeling on that. So I have also published a blog on Medium, which you can see here, and I'm also recording this video so that it can be more informative to all the audiences. So I will be explaining the project step by step, following the flow in this blog. And whenever required, we can switch to a code walkthrough, where also I'll be executing small snippets of code, which can kind of enhance the effect of this video. And we will also see the project commit by commit, or groups of commit, some groups of commits together, and we will proceed further. And whenever there is a nuance which has to be explained, I will pause there and explain that nuance, and we will just continue. So let's get started. So this project is called Sanskrit GPT, but it's ideally a GPT architecture or a transformer architecture, which can work with, which is ideally supposed to work with any language currently present on Earth, because this architecture processes the text character by character rather than tokens, or rather than words together. So let's get started, and along the way we will see what concepts have been used and what are the minor details and minute details we have to take care to make this project work, and we will just get started. So most of the modern LLMs use byte pair encoding or variants of the same to kind of convert the text in the way we understand letters, and those letters or bunch of letters are converted to some numbers using certain rules, and those certain rules are dictated by byte pair encoding algorithm. And since large language models, or any machine learning model for that matter, understand only numbers or dense vector of numbers, we have to convert the given text into certain tokens or certain number representations, and that is when you pass those numbers to the LLM. So now let's have a look at a popular website called Tokenizer and understand how tokenization works with respect to various modern LLM model, LLM architectures, and we will get back to this blog once we explore that bit in a moment. Yeah, so this is a popular website called as Tokenizer, and you can select various models and various tokenizers from this list given here. We will stick to GPT-4o to kind of do this exploration. So now here, let me just get some text, and we will see how it is being tokenized or converted into numbers. So this is the text I have put here, and some things which, so that actual text is seen from here till here. So whatever other stuff you can see in this prompt is actually a system level prompt, or let's say kind of supporting prompt in a way. So what this prompt tells is like what the LLM has to understand from the user's prompt, what is the intent of the user's input in this prompt, and what it has to return back as an output. So this kind of serves as a context, or as an encapsulation of the input prompt which is given by the user, and the model can understand what it has to extract and what it has to understand from that prompt. So your exact prompt, or the prompt which we have given here, is seen from here till here. Now, as you can see, the word most, like most, these group of characters are converted to one number, which is 14,046. After that, space and modern. So space character is also considered in that group of words together. So space modern is converted to token number 6809, and then there is space L from, so LLMs is one word, but to tokenize it, it is considering space and the first capital L. So that is converted to 451. Then there is L and M from the LLMs, the second L and the M, that is converted to 19,641, and the S is coming here individually, which is 82. So tokenizer actually kind of splits the input text into multiple smaller chunks, and these chunks are fed to the LLM one by one, and that LLM can kind of create a context around all of these tokens together and then do its processing, whatever output it has to give, and whatever output is expected by the user, and all of those kind of uh, tasks. So what exactly happens here? So what happens is when you are training an LLM, there is some certain data which you call as training data, and that training data or a subset of that training data is actually used to train this byte pair encoding algorithm also. So this byte pair encoding is not something which is predefined or static, or something which is a set of hard and fast rules. Byte pair encoding is actually very much dependent on the training data, and a subset of training data, or if the data set is small, the whole data set is used to train or used to condition this byte pair encoding, and that is how it understands which group of tokens belongs to what number. So, for example, in the training data set of probably GPT-4o, it has seen the word most appear many number of times. So, what it is suggesting is these MOST, this subset of words occurs more frequently in the data set. So let me group these together and let me assign it one unique number. So whenever this unique number is seen by the LLM, it understands that it is representing the word most, right? So there is a wonderful video which you can refer, which I refer to understand how tokenization works and what are the pitfalls of tokenization and many such things. So to understand tokenization in more detail, you can just have a look at this YouTube video. I'll just open that here. Yeah, so this is a wonderful video to understand how tokenization works and what are the pitfalls of modern tokenization, and what we should develop over time to kind of make the modern LLMs understand our text and in multiple languages, and extract more information from that text and kind of process it together. So this is a wonderful video. I'll give the link to this video in the description, but I'm assuming most of you are aware of this video, and you might have already watched it as well. So let's come back to the blog. Now, what exactly happens with morphologically rich languages like Sanskrit? There are Sanskrit and its let's say kind of daughter languages. Most of, or rather all the Indian languages have taken concepts from Sanskrit, and Sanskrit is kind of the mother language of almost all of the Indian languages which you see today. So in Sanskrit, what happens is there are words. There are two concepts where the understanding or the construction of words itself changes. So in English, let's say you have words like with, by, to, for, from, his, or belonging to him. His and belonging to him are kind of similar. Then in, on, within. So these words are actually prepositions, or they function as prepositions in the sentence. What is a preposition? So preposition actually tells you more about noun or something which is positioned with respect to the subject, or is of the subject, or belonging to the subject, or placed somewhere with respect to the subject. Maybe so within basically means within the subject. That also is a valid preposition. So these prepositions actually come up as separate words in English. Let's say let's take an example from here itself, or we can actually look at the translation. So there is a sentence from which I've taken from an epic from our Indian history, Ramayana. So Ramayana is a story of a prince who goes on an exile with his wife and brother, and he encounters many challenges and ultimately wins over all the challenges. This is a pretty prominent historical event in the Indian history, and this sentence is taken from that event. This is one sentence taken from that event. So let me read it out. Let's translate it and understand how the prepositions, English prepositions are, and then see what concept is involved in Sanskrit similar to prepositions. So this is here is reading of the sentence. Ramena Saha Sita Vanamasam Gacchati. So the whole sentence is Ramena Saha Sita Vanamasam Gacchati. So let's translate it. So exact translation would be along with Rama, Sita goes to Vanavasa or proceeds to Vanavasa. word to word translation would be Ramena. Ramena means with Rama. Saha is basically a word which can be used to denote together. Saha is together, kind of translates to together. Then Sita is his wife. Then Vanavasam is Vanavasa or exile. And Gachati is goes or proceeds. So now here you can see in English, the with and Rama are coming as two separate words or two separate entities, two distinct words. But with Rama is kind of represented with only one word in Sanskrit. So Ramena. Now, what happens here? Rama is the subject, but that sound of ena, the sound of ena is actually representation of with. So the preposition is actually appended to the word itself. So that is how we understand that Ramena means with Rama. Rama is a subject, a standalone subject, makes sense. But when you append the sound of ena to it, it becomes with Rama. Similarly, Vanavasam. So Vanavasa is the actual subject. Then when you kind of attach the sound, the sound, the dot on the top, so that is when it becomes Vanavasam. So in this context, it kind of denotes two Vanavasa. The function of the word two is denoted by the sound at the last. So Vanavasam Gachati proceeds or goes or proceeds. So as you saw here, the prepositions are attached to the subject itself. So this is one of the concepts in Sanskrit which we call as Vibhakti, which which kind of appends the function of preposition to the word itself. Now, let's put this sentence in Tokenizer and see what or how the GPT-4o kind of tokenizes it. So let's copy this and paste it here. So it is available from this part in this part. Now, as you can see, Ramena is split up into Rame and No. So if you highlight here, Rame is denoted by two numbers. This is I think 1,87,681 and then 628. And No is coming up as an individual word or individual token, which is represented by 4,986. So when Ramena was one word and it already had the information of the preposition as well. Still, GPT-4o's tokenizer is kind of splitting it. It is breaking it up and then it is doing the processing. But if you kind of look at it, if you just look at the highlighting of the text, Rame means Ramaha is the subject, but Rame means within Rama. So Rame denotes one other preposition and Ramena denotes other preposition. So Ramena means with Rama, but Rame means within Rama. So this kind of can create a confusion, though it does not create any confusion as such, but it can create a confusion when you look at it individually. Also, this split up does not really break the understanding of LLMs when you are conversing with them in Sanskrit or any other morphologically rich language. But what if we don't break these words and have these words processed as they are without breaking them up into non-contiguous and nonsensical chunks of subset of characters? Can we increase the understanding of the LLM with respect to these languages? So that is basically the question which I had asked when I started this project. So that was also the motivation to kind of design this whole architecture. Right? There are similar concepts in other Indian languages as well. So in Kannada, it is that is how we are taught Vibhakti in Kannada. So it kind of goes like a poem, so that it is easier to remember and you can directly relate to what word you are looking at and what Vibhakti you are using at that point. So it's called Prathama U and Vidya Anu and it proceeds. Then there is the same concept in Marathi as well, and then there is the same concept in Hindi as well. There should be these concepts in other Indian languages as well, but I personally know of these 4 languages, so I have put them up here. Then one more concept is called Sandhi. What is Sandhi? So let's say when two words are following each other, based on certain rules that govern this concept, the boundaries of these two words can be modified and these two words can be gelled together into one word. These two words can be merged together into one word. There are many types of Sandhi and there are many rules that govern this behavior, and this is a little involved topic. So let's understand this from a few examples. So let's take this example. Kako kashe viharati. So what does this mean? Kako kashe viharati means the crow flies in the sky. Now, the first word, kako kashe, can be split up into Kakaha and Akashe. So, and Viharati stays the same. So, Kakaha means the crow, Akashe means in the sky or within the sky, Viharati means flies or roams. So, Viharati has multiple meanings, but in this context, it means flies. So, Kakaha and Akashe, when they come together, there is a rule that says you can combine these two words together into Kako Kashe, right? So this is one example. There is one more example called, or one more example to depict this behavior is Bhubukshur Bhavati. So Bhubukshur Bhavati means he, she, or it is hungry based on the gender of the word which comes before this word. So Bhubukshur Bhavati can be split up into Bhubukshu Bhavati. Bhubukshu means hungry, Bhavati means is or becoming. So this is one more example of how the words can be modified in Sanskrit based on certain rules, and that is why you can actually have an infinite vocabulary of words in Sanskrit, and kind of counting these words becomes a very tedious task. So that is these two concepts are from Sanskrit are actually really important to address when you are training an LLM on Sanskrit text or any other Indian language, because all the Indian languages will have these concepts, right? So what exactly happens here? These concepts, as I mentioned before, don't exactly break LLMs, or you don't exactly get weird outputs because of this representation, or how the byte pair encoding breaks them into non-contiguous and nonsensical chunks. Why this happens is because the chunks are arranged in a contiguous fashion, and the LLM accepts all these chunks together and then kind of understands the context. So if you know how attention works, attention is quadratic. So every token is correlated, or we take a dot product in attention. So I'm using the word correlation here. So every token is correlated with each and every other token, and then a context is developed. So here what happens is Rame will be followed by na, and that is how the LLM understands that Ramena means with Rama. But let's say if we don't, we develop certain architecture and we make some changes to the data set, and let's say we can avoid splitting of this word into Rame and Na. Will the LLM understand this word better? That is basically the question that I'm trying to answer in this video and in this blog as well. So basically, our goal is to check, can we build a model that understands the hierarchy of the characters first, like how the word is constructed, and then after we understand the hierarchy of characters, we'll then understand the hierarchy of words, how they are arranged, and how the LLM can understand these things. So a far-fetched goal of this whole exercise is to kind of develop a conversational LLM in Sanskrit and other Indian languages, because there is so much knowledge and so much information available in our literature and our history that we will once we are able to consume all of those nuances and details and the knowledge in our literature, we will be able to connect the dots on how the society looked at that point, how the geological changes have happened in that region, how the society has evolved over time, what was the lifestyle of people in that region in the older times. All of these dots can be connected very easily, but consuming that much information at scale probably is not possible for a human being. So what I wanted to try here is to combine that massive ability of LLMs to consume a lot of information at scale and the knowledge from our ancient literature. When you club them together, we will be able to connect the dots and understand how the society has evolved in these literatures, and we will be able to answer a lot of open-ended questions which we have today. So whenever there is a topic you want to understand and you have a question-answer type of communication or conversation, you tend to understand that concept in a minute and let's say in a granular level, right? So that is the motivation I wanted to tell you, and why I'm trying to develop this project or the model. Now let's start with the actual project and see how the data is modified to get accepted by this model and what changes we have done to the model. So there is this data set called Sanskrit. So there is a website called sanskritsahitya.com, and the data which is shown on that website is all collected in a form of a repository and kept on GitHub. So let's have a look at that dataset. So this is the dataset, and this is published by Antariksh. A very good dataset and phenomenal effort of developing such a structured dataset. I think this dataset was actually developed for computational linguistics, but for me, I could just get started with this dataset very easily for my project as well. So this dataset is structured really nicely, and it's very easy to understand. I'll tell you what I mean by structured when we look at one of the data points. So each and every literature has a directory of its own with the name of the literature as the directory name. And within these directories, there are multiple JSON files which have the actual text representation. So let's open one of the data points and I'll show you. Right. So this is the data set. So these numbers are actually really helpful when you want to understand this data set in a structured format. So uh, Sanskrit is actually written in verses. Like there are there is a verse number, and these numbers which I'm highlighting here actually, I think they point to the location in that literature where these verses occur, and it is beneficial to check how these numbers are actually serving that purpose. But in my practical use case, I didn't really need these numbers to be used. My major attention was focused here. So this is the actual text. This is Sanskrit language written in the Devanagari script. So I have written a snippet to kind of extract these verses from this JSON file, and I have kind of parsed through all the directories and have developed one huge continuous stream of words which I kind of chunk later for easier consumption by the model. So we can have a look at that snippet as well. So I'll just show you the snippet. Let's open, let's see the numbers up here. Right. So it took a lot of time actually. I don't know why that happened. But anyways, so I have written a snippet to kind of extract the verses from the JSON files, and I am attaching all of those sentences together to form one huge continuous stream of sentences. And after each and every document or each and every literature ends, I am attaching a end of document token to represent that the document has ended here and the next document will start. Also, I am extracting this. We can have a look here as well. So I am extracting the data where I am grouping the words together. So in Sanskrit, space character is the delimiter. So after space, like one word, then space, and then the new word starts. So space acts as a delimiter or the separation between two words. So I am splitting that huge sentence at space, and I'm collecting the words together. I'm not splitting these words in any format. I'm taking the whole word as one token representation. And after that, while I was doing exploration on this data set, I found that the longest word is actually of 123 characters. And with the start token and the end token, it becomes 125 characters. So I am padding all the words which I have collected to length of 128 words, and the remaining length is considered with padding, like is appended with padding. So a word is represented like this. The start of the word token is added, then the characters which are appearing in that word, then the end of word token, and then if there is remaining length to achieve the length of 128, that is achieved using padding of the word. Right. So after this exercise, I am storing the whole data set as an NumPy array, and after this, I am actually sharding them. So what happens is you cannot pass the whole huge chunk to the machine learning model and expect it to learn, because that will be very inefficient. So what I'm doing is from that huge contiguous stream of words, I am choosing 32 words to become one sentence and one sequence, and 16 such sequences are considered, and that whole thing is one batch or one shard. So I am sharding the whole data set as well, and those sharded data sets are also stored as NumPy arrays, right? So let's go back to the blog. So that is how the data set is being used and modified to match the nuances of our architecture. So I personally am using this commit ID of the project. I when I downloaded or when I cloned this repository, this was the latest master. After this, many changes have gone in the repository to correct the mistakes that might have occurred due to different fonts and different formatting. But I personally had made a lot of local changes in my setup. So I just continued using this commit ID and I proceeded with creating my project around this, right? So before we dive into the project, let's actually have a look at the research papers from the literature of this domain. So there are some phenomenal works which have already been done in this domain, and I have referred 5 papers altogether. 2 of them are from Google, and 2 of them are from Meta, and one of them is from Rice University. So I have attached the links to the papers in this blog itself. You can have a look at the papers. These are some of the best works done in this domain, and I have presented my thoughts on these papers in the blog. So we will be going through these papers in brief in this video itself. So the first paper is which we will be looking at is CANINE. So CANINE is from Google. CANINE is actually one of the first works where they have represented the hierarchical fashion of the transformer architecture. So this architecture is actually trained on the characters. So let's say you give this architecture this sentence. If you look at it as T, H, E, space, A, R, C, and so on. So what they do is they convert these characters to their Unicode code points. So now what is Unicode code point? I'll just show you one example and let's check how they look. So Python gives us a set of functions which help us to develop a one-to-one invertible mapping of characters to a unique integer or a unique number. So let me just activate my Panda environment. Right, so let's go to Python and let's say we want to get the integer that represents the character of A, small a. So it returns 97. Let's check E maybe 101. Let's check Z. Let's also check something from the Sanskrit text. Let's say I take from Ra. Right, let me print it here. Okay, this given error because Ra is not a single character, it is made up of 2 characters. So let's put up a for loop here. Right, let's print this. So this is what happens. So Ra, like the first syllable or the first character in Ra is actually represented by 2352, and the straight line, which you can see as the second character, is represented by 2366. Let's now actually do the inverse of this process. So that function is chr, and let's say if I pass 2352, it will print R, and if I pass 2366, it will print the straight line. Let's actually see it for the integer parameter. Let's say I pass 97, it prints A, right? So this is an invertible one-to-one mapping, which is really helpful in many ways, and I think most of the literature which works on character level actually uses these concepts, right? So going back to CANINE, so this is the first step. This is the first step that happens here. It accepts the text in the form of characters, converts it into numbers. Now they pass it to an embedding function. So they have multiple embedding functions, and all of those embedding functions accept one character at one point, and they return a vector representation of that character. And they have multiple such embedding functions. So they get these vectors from each and every embedding function. They concatenate them together, and they create a huge vector representation of that character. So that character is represented by this huge vector. So multiple such vectors are representation of a word and so on, word and then words and then sentences. So Once they have this representation, they pass this representation through a single local transformer. So a single local transformer is not the encoder decoder form of transformer. It is actually a bunch of attention layers, birth kind of attention layers, and they pass the representation through this single layer transformer. Then they pass this representation, this richer representation through a strided convolution. Why do they do that? This representation can become this representation can grow in size exponentially, or not exponentially at least, but linearly, but in a very quick way, because you are consuming the text in form of characters and not words, right? So this representation can explode very quickly as the sequence length increases. So they pass this richer representation through convolutional layers to kind of control this explosion of the size. And once they have this convoluted representation of the text or the actual input text, they pass it through a deep transformer stack. So what does a deep transformer stack do? Let's check what an LLM does. So let's say you pass the sentence, the cat sat on the. So now, since this example is used widely, you would expect the word as mat, right? The cat sat on the mat. So LLM's function here is to consume the first tokens as context and then generate the word mat as the output. So this is called as sequential modeling or language modeling. So this deep transformer stack does exactly that, but on this convoluted representation of text. And once they get the output from this deep transformer stack, they use it in two tasks. One task is the classification. So they can classify the given sentence into multiple categories. A very basic example for that is sentiment analysis. So they use the representation which occurs at the position 0, and they name it as YCLS. YCLS stands for Y classification. So the second way in which they use this representation is they kind of use it in an MLM task. So in MLM task, what happens is you kind of mask some characters from some words, and the model should auto-regressively predict what character is the best fit in those masked out spaces, or the bland out spaces. So that is the second task in which they use. So the final, so the output which comes from the deep transformer stack is passed to an upsampling function, and then finally one more single transformer module, and then they get the Y sequential output, or the final representation of the characters for sequential tasks. So this paper came out in 2021, and I think this is one of the first ones to show that transformers can be used in a hierarchical fashion. So I have taken inspiration for my architecture from CANINE itself, with some changes, of course. So that is the first paper which I had read to understand how these models can be designed. So the next paper is Byte. So Byte is an extension to the MT5 architecture. So MT5 is an extension of a T5 architecture. So MT5 is multilingual T5, and Byte is actually the MT5 architecture working on bytes, right? The directly on bytes rather than tokens itself. So what exactly is byte? Let's just see if we can actually get the representation in bytes. So let's take a string. Let's take ra itself. Yeah. So string has a option called encode, if I remember correctly, and you pass the scheme here, right? So now ra is actually represented in form of bytes using this sequence of bytes. I think this is an hexadecimal, and because there is a slash x here, but you can actually get so all of the bytes range from the values 0 to 255, and a bunch of them together represent characters like ra, or represent strings basically, but they can represent characters as well. So Byte is actually working on these bytes individually, right? Instead of combining bytes together to form one token, every byte here is becomes a token in itself. So that is how Byte paper is doing its processing. They have made some architectural changes to match this change in the input data from tokens to bytes. And one more architectural decision which they have taken is that the encoder is actually 3 times heavier or 3 times deeper than the decoder. So what they claim is that since you are encoding text in the form of bytes, encoding actually requires a lot more compute than decoding. So this is their intuition to keep the encoder heavier. And this decision is also visible in my architecture. In my architecture, the character encoder is deeper or heavier than the character decoder. Right. So these two papers, even Byte is from Google, and I think it also came out around the same time as CANINE. I think a year later. So yeah, those two papers are from Google. And next paper is from Meta. It's called Megabyte, and Megabyte is basically a combination of CANINE and Byte. So Megabyte is actually a hierarchical architecture, but it works on bytes. So what they do is they accept a stream of text in form of bytes, and they have something called as a patch embedder. So what a patch embedder does is it splits the stream of contiguous bytes into groups of patches. So every uh, patch is like a subgroup of bytes, but they are not based on any rule. Like I think they have only one rule, that they should be equal length of patches, irrespective of how much ever the actual length was. So let's say you have n number of bytes. All of these are converted into k patches, and every patch will have n by k bytes. So these patches act as tokens to the final to the deep transformer stack kind of model which we saw in CANINE, and after that it does the sequential modeling or the language modeling, and finally we have a small decoder architecture which kind of accepts the context from the deep transformer stack kind of model, and it auto-regressively splits this patch into their constituent bytes, right? The constituent bytes meaning what would come after the given text in form of bytes, right? So that is what Megabyte does. A similar paper is called Space Byte. So this is from Rice University and is kind of a development on Megabyte's work. So here they have architected the model using the intuition that once you predict the first character or the first byte in the given patch, predicting the subsequent bytes becomes very easy, right? But predicting that first byte or first character itself is very difficult, significantly harder. So they kind of try to put more compute to predict the first byte or the first character, and the subsequent bytes or characters are even lesser compute, kind of. Right? So that is the space bytes development on top of Megabyte. So the last paper is byte latent transformer, and this came out very recently. I think it came out in 2025 December, and it is work on top of space byte and Megabyte. So what happens here is the main thing which is important here is what we understood in Megabyte is that the patch has to be of fixed size, but in byte latent transformer, patches can be of arbitrary length, and that length is actually decided by the data itself, and kind of I think the model also plays a part. I'm not exactly sure about that. I might have to run through the paper, but this is to quote from the paper directly. Patches are segmented based on the entropy of the next byte, allocating more compute and model capacity where increased data complexity demands it. So the patches are designed, or the patch boundaries are designed based on the entropy of the next byte. So let's say the entropy of the next byte is significantly higher than the some previous uh, bytes. Those bytes are considered as one patch, or one segment, or one token, or one token representation, and after that boundary the next group of bytes start. So that is how they have kind of uh, achieved a dynamic way of splitting patches into or rather splitting the contiguous stream into arbitrary length patches. This paper is a little complex, and it might require a deep dive and a blog of its own. So we will stop here, and we will get back to the project in the next section. So hi guys, we'll continue our session from where we left in the last session. So we completed the paper explanation in a brief way, and we'll continue from there. So as you all know, there are many LLMs available currently that help you guide through the projects and help you understand some concepts via a question answer type conversation. So I have used Gemini predominantly in this project, and it has been very helpful and an amazing co-pilot. So I have used the Flash and Pro versions, Gemini 2.5 Flash and Pro versions in this project. So around 40% of code was suggested and generated by Gemini, and Gemini has helped me understand the nuances of attention, padding, tokenization, TensorFlow APIs, and how to convert Python, a combination of Python and TensorFlow into TensorFlow specific or TensorFlow graph compatible code, so that you can increase the resource utilization and all of these concepts, right? So as I already mentioned, back and forth question answer sessions help you understand the concepts in a very deeper way, right? So Gemini has been my conversation partner in this, and it has helped me understand all of these concepts in a deeper fashion. That was my co-pilot. So let's get started with the project right now. So as we've already seen, we have taken the data set and we have converted the data set into multiple shards or multiple sub or some multiple mini batches. And the words have length of 128 with the word structure being the start token, the characters in the word, the end token, and if there is any length remaining, it will be added with padding tokens up till the length of 128. So there is a pictorial representation also here. Let me just go there. So this is how the word is represented. Of course, this is a vector representation of all the characters. Will come till there, but this is how if you squeeze all of these vectors into 1D, that is how the word will look. So the start token is ST, then the characters are present, then the end token is there, and then padding tokens are present up till the length 128. Right. So now here I had to make a choice whether my model will have an embedding layer or not. So with an embedding layer, your task of language modeling converts to a token classification problem. But if you don't have an embedding architecture, you don't have an embedding layer in your architecture, then it becomes a regression problem where you convert all of these characters to the dense vector representations, and finally get dense vectors as output itself, and then you perform a regression on these characters, and they have to match the training data set vector representations, which you actually pass as labels, right? So now we have around 304 unique Unicode code points in the Devanagari script, but only 128 of them are massively used. So what I thought is, instead of having an embedding layer, let's convert this task into a regression task, right? So given a character or its Unicode code point, I'll convert that into a vector, and that vector will be used for regression tasks, and the model will be trained using the regression concept, right? So now how do I convert the character into a vector? Because I don't have an embedding layer. Embedding basically serves that purpose itself. You give a index, it will return the vector representation of that index or that character. But now, since I am choosing not to have an embedding layer, how do I convert these characters into the dense vectors? So if you remember, in attention, there is one vector which we use or one tensor which we use multiple times, and that is generated based on a formula given one value, that is positional encoding. So now positional encoding, what happens is, you have a tensor, and let's say you query the position vector at this position, it will return you the dense vector representation of that position. So yeah, we have something which can accept integer and return you a dense vector representation. But the problem here is positional vectors are not reversible. So let's say that you get the vectors from the model, and you want to convert those vectors back to the integer representation. That is where you will hit a wall, because since the positional vectors or the positional encoding is based on sine and cosine functions, because of their cyclic nature, let's say you generate a positional, or let's say you generate a dense vector using the positional encoding concept for the value 10, and you try to reverse it using arc sine and arc cos, or sine inverse and cosine inverse functions. You may or may not get 10, because the way they are put together in that formula of predicting the positional encoding. So this was a problem. So I asked Gemini for a solution here, and the problem statement was to generate a mathematical function that takes two arguments. First argument is the dimension of the vector, or how large I want the vector to be, and secondly the value for which I want to generate the vector or the dense vector representation. So Gemini gave a very nice function, mathematical function, which I have put here. So you can go through this in the blog itself. So now we have the mathematical function which can convert a given integer to its dense vector representation. So now the architecture looks something like this. So there is an input tensor with of size, batch size, then number of words, then the word length, then the character dim, like the length of the dense vector representation of each and every integer or character. That is passed through a transformer encoder. Then the transformer encoder is kind of called in a loop over all the batches, and that converts this vector representation, this tensor representation into a uh, into a 3D tensor where the size is batch, number of words, and word dim. So as you can see, this word and this character dim are kind of fused together, and here this word dim is basically the dense vector representation of each and every word, not character, each and every word, right? So this 3D tensor is passed on to a global transformer decoder where it does its sequential modeling or the language modeling, and it gives the same 3D, same size 3D tensor, which is batch size, number of words, word dim, and then it is passed on to a transformer decoder where this transformer decoder is again called in a loop, and that loop basically predicts the words one by one based on or rather it predicts the words character by character in an autoregressive fashion. So the transformer decoder has multi-head attention, then context decoder attention, and feed forward. So this context is coming from the global transformer, and it is conditioned based on the previous characters which are used to predict the next character in training. In inference, that connection is removed, right? So we will go through the code to understand better how this architecture works, right? So let's go to the code now, and let's I think we have to go one more commit to the next commit to actually see the whole architecture in a proper shape. So let's just load this, and we should have the model here, right? Yeah. So this is the model or the architecture which you saw in the blog, right? So this has character encoder, this has the word backbone, and the character decoder. So character encoder is this transformer encoder. The word backbone is this global transformer decoder, and the character decoder is this character transformer decoder, which is at the extreme right in the architecture, right? So now how are these combined together? So you have a character encoder being called for all the batches, like batch by batch over here, and then you concatenate all of them together to create that 3D tensor. Then this word embedded tensor, which is 3D tensor, is passed on to the word backbone to does the do the sequential modeling or the language modeling task, and this representation serves as the context for the character decoder. Now character decoder accepts two inputs. Why? Because you will now, if you know how attention works, attention basically kind of takes the first n minus 1 characters, then there is a context vector with which the cross attention happens, and it predicts the next 127 characters, right? Which on next 127 characters, and that is how it is trained. Let me see if I can explain you in a better way here itself. Let's just say attention expectation. So what happens is it accepts the first 127 characters, and that is kind of you do a cross attention with the context, and it predicts what will come here, 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 and all the way till 127. These are of course positions. Actually what happens is this is 1, this is 2, this is 3, this is 4, and this is 128, right? So with when you have first character and you have context, what will appear in the next position. So ideally, if you, so this also serves as the training data when you actually train the model and you calculate the loss function and the last layer. So this is actually matched with these what you say characters or the vectors here, and that is how the transformer understands that given these characters and given this context, these are the next set of characters that I should predict, right? So with respect to 0 and context, 1 should appear at the next position. Then you consume 0 and 1 together, and then when it is conditioned with context, you expect 2 to be in the position. Then when you accept the first 4 characters and condition them with context, what should appear at the next position, which is the 4th position. So that is how attention works, and character decoder actually accepts those things only. It accepts the first 127 characters of each word, and it is conditioned with the words which are coming from the word backbone, and it predicts the words with next 127 characters as the output. So then you have the output here, and that is how the model is being trained, right? So I think I have written train.py also now. Yes. So now here multiple masking strategies are used, and then we calculate the MSE loss, because remember we don't have the embedding layer, and now the task is shifted from the token classification problem to actually vector regression problem. So vectors are supposed to match the vectors from the training data. So that is what is happening here, and the training just proceeds. So let's go back to the blog and continue our journey in the blog itself. So now, one more thing is how I am encoding, or rather converting the given characters to the vectors, right? So the function which Jamina had given is present in this encoding.py, and I am actually taking all the shards. Then I am flattening the shards. Then I'm passing them to the vector integer to vector function. And when you want to kind of invert this, or reverse map this vector to an integer, you can use this. There is, I think, vector to integer function here itself, which will return you back the integer. So then we create something called as embedded shards, and these embedded shards are actually used in this train.py function, train.py file. Right. So let's go back to the blog. Now this function is actually pretty fast, and since this does not have any learnable parameters, the training stops the layer right next to this, right? So this layer need not be trained. This is a deterministic function, and it is since it is a deterministic function, it is pretty fast, and because it does not need back propagation and all of those things, right? So finally, when you pass this word or the set of Unicode code points to this function, this is how the word is represented. The start token vector, then the Unicode, the vector assigned, or the vector which is coming from that function with respect to this integer 2330, then the next vector for 2367 all the way till the end token vector, then the padding vector up, all the way till 128, right? Now, let's have a look at the actual attention on formula, and how this vector representation fits into that attention formula, right? So attention formula is the query vector multiplied with the transpose of the key vector plus whatever attention mask you have, whether it is to ignore the padding, whether it is to model autoregressive predictions and all of that. And once you do this, you do a softmax to finally get the probability representation of the entire attention values, and then you multiply it with the value vector. I have dropped the under root d thing just to since it is a constant, I have just ignored it, but that also plays its part here. I have just ignored it for simplicity. Now let's actually try to insert this vector in this formula. So Q looks like this: the start token, the first character vector, the second character vector, all the way till the end character end token vector, and then padding vectors. Then this is an encoder representation of the attention. So query, key, and value are all the same vectors actually, right? So then you do a key transpose here, then you get the transpose of the same vector, and then you do a query into key transpose, and that is when you do this, and you get this tensor as the final output. This is 128 cross 128 because the multiplication is actually happening on the embedding dimension, or the character dim dimension, which I showed before, right? So now ST into ST is ST star, which is correct. ST into C1 is basically conditioning how the start token or the start vector is connected to the first character vector. ST into C2 is first start vector, how it is connected with the second character. This is all fine up till the end character, but the moment you have PT or the padding token vector, it is not necessary to actually have these. These can all be masked, because when you padding tokens do not have any inherent information with them. They are just a representation that the word has entered, and I am just padding the vector to certain length to make the resource utilization more. Because if you know, GPUs kind of work very nicely, and they are utilized very nicely when the representation or the tensor sizes have powers of 2 in them, right? So that was the motivation to pad these vectors up till the length 128, and also second motivation to not have ragged tensors or jagged representation of tensors, because words can be of arbitrary length. So you have to pad these arbitrary lengths to 128 for even the matrix multiplication to happen in a proper way. So these have to be masked. So whatever I have marked with red, right? These are actually the dot products which are taken when a valid token is when a valid token and a padding token have a dot product between them, or a padding token and a padding token have a dot product between them. Padding token and padding token actually does not even make sense because there is absolutely no information available in that dot product. So how do you generate the mask here? This is a very weird mask, right? Because you don't have like a whole column of information, some set of columns with all the information, and then the columns with no information at all. So it is not like split up into vertical parts, or it is not even split up in like horizontal parts. It's a very weird tensor where the actual information is captured in the top left of the scores matrix, and everything else is padding, or everything else is either padding or token valid token and padding. So all of these have to be masked. So this is how the mask actually looks. These are zeros, and all of the others are ones which you actually have to mask, and that is multiplied with negative infinity, and you finally do this, right? Scores plus mask, and that is what is happening here. Scores plus mask, the scores remain intact, and all the other values become in negative infinity. Now the first problem here is construction of this mask is more complicated than it needs to be. So I have given the code here. It can actually be simplified, I think, but this is where I stopped simplifying it and I kept it as it is. Second problem is when you apply softmax. Softmax requires a dimension because it has to kind of zero out the negative infinity values and scale the actual information bits or the information values. So when you do a softmax here, this all becomes nan, and nan are really dangerous to the training process, because whenever you encounter a nan in the training process, gradients also become nan, and the whole training pipeline is corrupted. So this is what happens. I'll also run this code live just to show you. Let's just go here and run this, right? Let's go here and code. So let me report it actually. This simplification method that I'm and I'm creating here dot answer what am I doing? Here dot answer here dot once, and then 2,5, and I think I'm multiplying this with here dot answer with negative infinity. So let's print this tensor and see. Yeah. So if you see here, this is in all are in. So which is basically a representation of this one only. You can transpose it and get the other representation, but let's just think that it is this representation, the second and third rows representation here, right? All in. So next thing what I'm doing is I am doing a softmax on this with access. So let's just do softmax tensor equal to bf dot and then next bf dot softmax. I'm passing the tensor, and access is given as -1. So let's print the softmax tensor. So as you can see here, these are all nans. Encountering nans is, as I mentioned, is very it's not desirable because it corrupts the whole training pipeline, right? So here also you can avoid this by creating a custom softmax function where wherever it says like a column of infinities, negative infinities, or rows of columns of negative infinities or rows of negative infinities, it will, instead of giving out nans, it will give out zeros. So I had actually implemented this with Gemini's help, and I will just show you that function. Yeah, so the save softmax, basically what it does is it uses a tf.where, and wherever it sees like nans, it will replace it with zeros, zeros in those in place of those nan values. But I was not really convinced to use this function because the complexity at this point was increasing exponentially. So what I did was I removed all of these things. I just kept the masking, content-based masking as it is. So this is what I call content-based masking, because the masking is actually based on content rather than it being based on any rule, hard pass rule. It is based on content, right? So I had this for encoder, I had it for decoder as well. Decoder is actually more complicated because instead of having zeros here, you need to have a triangular matrix, because in decoder you actually have to do the autoregressive modeling, right? So it is more complicated, so I have not put it in the blog, but it's present in the code base. You can have a look at it in the code base. So I had those masking mechanisms in place, right? So now after even masking attention, you have one more problem. So how does attention look? So let's have a look at the actual attention formula or the architecture, right? So if you go here and look at the architecture, so if you see here, you have this residual add, right? You are taking, you are doing the attention calculation here with all of those maskings which I already showed before. But now you are doing a add and norm here. So you are reintroducing the padding tokens again. But when you reintroduce the padding tokens, many words won't have the length of 125 in the tensor length of 128. So what happens is, usually words are small, either of length 4, 5, 10. When you compare it to 128, you have only 10 actual tokens, but you have 128 padding tokens. So when you pass this to a feed-forward neural network in the attention mechanism, the feed-forward neural network sees more padding tokens than the actual valid tokens. So these padding tokens are actually noise which can ruin the training in a very bad way, right? Like the model will learn to predict the noise rather than to predict the tokens. It learns the noise rather than learning the tokens, right? So now you will have to introduce masking before feed-forward neural network as well. But handling these masks was becoming difficult for me. So what I did was I took a shortcut, which I shouldn't have taken, but at that point I was frustrated and I took the shortcut of trusting the backpropagation implementation of TensorFlow. So what I did was, in the final calculation of loss, right? If you remember seeing it here, I have masked MSE loss. So what is mask doing here? It will ignore the padding tokens from the training data set. So training with respect to training data set, I'm creating a mask to avoid the padding tokens, and I will calculate the mask only for the valid tokens. So now when you do like this, I hope that backpropagation can send this information in the graph or in the model upwards to help the operators ignore the padding tokens with respect to whatever is calculated for the loss. So in the loss you are avoiding padding tokens. I assumed that the same information will be passed on to all the operators in the model via backpropagation and tell them to avoid padding tokens at that level as well, right? So it worked for a smaller experimental data set. So I was like, okay, we have achieved the training properly, and now the task is clear. Train the model with the setup and generate the vectors, and once you generate the vectors, you pass them to the vector to integer inverse function, and you have your next characters predicted, right? And since I am kind of not using an embedding layer and softmax, the model is very light, and you don't have to expand the embedding layer also to incorporate more languages, because you already have that deterministic function which gives you the vectors given the characters, right? So we have the setup, but when I actually trained it for the whole data set across multiple epochs, the model did not learn anything, and the loss it decreased from the start till one value, and it started to hover around that value, and that decrease was not significant. So it started to hover around that value, and I tried to generate some text from that state of model, and it generated gibberish. So gibberish in the sense it did not make any sense, because to the input language of Sanskrit, it was predicting tokens or it was predicting characters in some other script itself, because of how the vectors were being generated, and those vectors being passed on to that vector to integer function. It was predicting Unicode code points of some other script itself. So it did not learn anything, right? So this was like the first dead end I hit while this project was in progress. Now I had to remove padding in some way, because padding was introducing noise, and I did not want noise in my training uh, pipeline, right? So what I did was, I looked at some more tensor types in TensorFlow. So TensorFlow has something called as a tensor type called as RAG tensor. You can create this RAG tensor, and you can actually have what RAG tensor means is, you can have a tensor which is not a rectangular format or a cube format. You can have a tensor which batch size as some constant number, but internally the batches or the sequences can be of different lengths. So let's say the you have a batch of words and the word lengths are varying from 3 to 10, and you have not padded it. You are using the actual sequence length itself. So you can create a ragged tensor which looks something like this: batch size question mark, which represents the ragged tensor length, and the D representing the dimension of the characters, right? Now, these tensors work perfectly in theory because you are actually doing a matrix multiplication, and matrix multiplication will work on the final column, right? The last column, and the last column is deterministic, or the last column is fixed because it is a dimension, it is a what you say, it is a embedding dimension or the vector dimension which is representing the characters. So all the matmals happen perfectly, and you get what you require when you do it on paper, right? When you actually do the matmal on paper, you get what you require to train the model. So I assumed I had solved it, right? But at this point, I was using the tensor APIs like tf.map function instead of for loops, and tf.scan instead of while loops. So what happened is these functions actually help you utilize your resource, your GPU or CPU, whichever your device you're training on, more efficiently, because these functions are actually TensorFlow optimized functions for that specific device. So instead of Python for loop, TensorFlow does not really understand how to optimize Python for loop. So when you replace that Python for loop with a tf underscore map tf dot map underscore function, TensorFlow now understands, okay, this is a for loop and I have to optimize it in this way. They have specific kernels for specific devices to optimize these APIs. So I was using, at this point, I was using these APIs, and unfortunately, these APIs did not have kernel implementation for RAG tensor on GPUs, right? You will end up with this error if you actually try to pass a RAG tensor to a tf.map function. So what it says is, it gives you an internal error, and it says no unary variant or unary op function found for zeros like variant type RAG tensor variant for device GPUs. So internally, for some optimizations, it kind of initializes a zeros tensor, and TensorFlow has a function called zeros like. So what it does is, when you have a tensor representation and you pass that tensor to a function tf.zeros like, it will take all the properties of the tensor like data type, size, memory layout, and device. All of these properties are taken, but the actual values in that tensor are zeros. So that is the function of zeros like. So that implementation was not available for GPUs for a RAG tensor. So we again hit a dead end here, but you can actually fix this fix this problem by running the function which is using tf function on CPU. So you can scope this function with this tf.device CPU, and you can run this. So CPU has an implementation, and I was able to pass RAG tensor to tf.map underscore function, and it ran. But the problem now is you are switching devices, right? When TensorFlow compiles one graph of a model, it likes to have everything, the whole graph, on one device, so that it can utilize that device very efficiently. But now, since you are splitting the graph, or you're breaking the graph and you're switching the devices, that switch requires transfer of data from the VRAM of GPU to the RAM, which is utilized by CPU. So this transfer takes a lot of time, and it will have drastic effects on your resource utilization, right? Your training can actually slow down because you are switching devices like this, right? So this switch can actually, and since this is a heavy operation, the most of the operation will run on CPU now. So this GPU is idle, and CPU will take a lot of time to train. So it will actually take an eternity to train on such a large data set, right? So I gave up the usage of RAG tensors also at this point, and I wanted to explore some more ways of having this uh, having this architecture work with variable length words. Before going to the next step, let's actually try to see if I can reproduce this error to show you how it occurs in a live session. Hey guys, so as promised, I'll try to reproduce this error in a live coding session as I said before. So there was an electricity outage, so that session had to be stopped abruptly. But let's continue where we left off. Let me try to show you how to reproduce this error, and we'll also try to fix it. by scoping it in this tf.device CPU, and we'll proceed from there. So this is the commit where that error was seen, and now I'll try to just introduce that. So let me show you the place where it is coming from. So it is coming from this tf.map underscore fn, where this will run on a GPU now, because I commented this line out where it would actually run this part of code on a CPU. So let's try to run this and write it to a file so that we will be able to look at the error. So let's just wait for some time. It will take some time to come to that point and error out. Right. So as you can see, it is erroring out in line 46 in this model.py, and it is dealing with this tf.map underscore pattern. So it is exactly this part. So let's now scope this inside the CPU device scope, and let's run this again. Let's write it to a different file so that we'll be able to observe it. Let's actually try to look at the GPU as well. So this is the GPU, and the model is just loaded, and it is trying to execute the model. And after some time, you will see a dip in the occupation of the GPU, because it will again error out with a different error, of course, not the same error. So here is the error out. Let's just remove this file. Yeah. So now, as you can see here, we are not seeing the same error. Let me open this side by side. So here we were seeing the error on 946, but here we are seeing the error on 966, which means it has crossed that part where it used to error out, and that function was actually running on the CPU. So 966 is actually where you are calling the character decoder. So it was able to successfully run the character encoder, the word backbone, and it failed out at the, or it errored out at the character decoder, right? So let me just delete this extra file so that all this will cost properly. So let's proceed. Let's go back to the blog. Yeah, so now I didn't want to fix that error, because working with rank answers was becoming really difficult, and I was looking at some different alternatives to kind of work with variable sized words and variable sized inputs. So as you already saw in the code, I have introduced something called as character RNN, right? So character RNN is basically it works on the word input, and it kind of tries to create a context vector out of that word and pass it on to the word backbone, right? So now let's actually move the code base a little further, and let's see what we have in the code base. Okay, looks like there are some conflicts. Let me see what those conflicts are. Actually, I'll change this. Let me start these, and let me continue the details. Yeah, parent training, right? So now I think this is just a restructure with a mask introduced to the character encoder. Let's have a look at the character encoder, how it looks at this point. Yeah, so the character encoder has a sequence of encoder layers, and these encoder layers are actually made up of encoder layers are here. Yeah, so the encoder layers are actually made up of a series of character RNNs, then followed by a feed-forward neural network, and there are two-layer normalizations. So this kind of looks like the attention architecture itself, where if you look at this transformer encoder, it has attention, it has add and norm, it has a feed-forward, and then one more add and norm. So it's basically the same thing, but instead of this attention, I have these character RNNs here, right? These character RNNs. So you pass the tensor through character RNN, and then you pass it through layer norm, and then you pass it through the feed-forward neural network, and then you again pass it through a layer norm, which is basically this. You pass it through attention. In my case, it is character RNN, then add norm, then feed-forward, then one more add norm. So this is basically how the character encoder is created, right? So now let's actually move forward till the greatest commit of what we have here. So we will be concluding the next part in this video, and then go forward with explaining whatever generation we did with this model, token generation we did with this model. And yeah, so before we actually go through the model architecture itself, at this point I would like to show you how I included the B.16 data type in this entire model run. So there is this file here. Yeah. So this API, Keras mixed precision global set policy mixed B.16. So what this tells is this tells the Keras front end, and we are using TensorFlow as the backend to Keras. So it tells Keras and TensorFlow to kind of do the computations in BF16, which increases the speed of the training, and it still stores or accumulates the final answer in FP32 or Float32 to ensure the numerical stability, and to also ensure that the accuracy remains, there is no precision loss during the training, right? So there are some operators which are very sensitive to these data type changes, and softmax is one of them. So I'll just show you that I have also kept softmax as it is. So let's go to the softmax part. It should be somewhere here only. Okay. Yeah. So here as you can see, what that does is that policy actually translates till the deepest layer which is available in the model, and it tries to do all the computations that are involved in B.16. But it is recommended that you do softmax in Float32 or in a higher precision to keep the training numerically stable, and also to keep the accuracy intact. So all of these functions of these computations actually happen in B.16, and then I'm actually casting the scaled attention logics to Float32. Then I'm doing the softmax here, and then again I'm casting it back to B.16. So my primary motivation of doing or having a B.16 training was to make the model smaller, so that I could actually increase the embedding dimension, or I could actually increase the number of parameters in the model so that the model can learn effectively. But when I read more about this policy, right, it actually didn't make sense to me that it actually decreases the model size, because the accumulation or the computations result is still being stored as FP32, though the computation is being done in DF16. However, after introducing this policy, I was able to make the model slightly heavier in terms of number of parameters, so it somehow turned out beneficial to my training. It also uh, made the training faster, and I was able to kind of train the model in lesser number of days. So usually without this API, I used to take 1 week to run one epoch. But with this policy, I think I took around 5.5 days to run one full epoch over one whole data set. So I was able to run for about one full data set and 20% of the data set in the second epoch, and that is where I stopped the training, because I shot over my compute budget on the GCP instance, right? So that we'll cover later, of course. So let's go back to the blog, and let's continue from there. So now to handle this variable length words or variable length data set, I got back the RNNs or recurrent neural networks. So by default, the implementation in TensorFlow of recurrent neural networks also does not support variable length tensors or RAG tensors, right? You will still have to pad the tensors up till one certain length, and only then you will be able to use RNNs, and RNNs also will kind of look at the padding tokens and try to learn them or predict them, right? So instead of that, what I did was I created an RNN implementation from scratch with Gemini's help. And what I'm doing here is there is a API called tf.scan, which takes three major inputs. One is the recurrent step, one is the actual tensors which you are performing the recurrent step on, and the initializer, which acts as the initial buffer or the initial storage where you store the result of this recurrent step, which is done on these tensors. That is, I think, how it is implemented. So let's go through this in the code, and I'll explain it to you line by line what those mean, right? So this is how it is. So the recurrent step actually accepts one previous context and the actual tensors. So here the tensors, there are two tensors which are involved. One is the word itself, and one is the mask. So these go in together like as one argument. So you'll have to split them up here as we do a normal splitting in Python. Then I am having a dense layer here which works on the character embedding, and there is one more uh, dense layer which works on the previous context. So once these two are done, what we do is up till a certain length, like till where the masking is valid, or till where you are supposed to pay attention to each and every character, till that time we will do this operation where you are kind of averaging over, or you're kind of adding over the previous vector representation of characters to the current vector representation, and that is being propagated till the last valid character. So what you do is, let's say now the word is this, right, which we had seen before. Let's say the word is this. So what you do is you perform a linear operation, or a TensorFlow dense operation on this vector. Then you keep this as the context for the next vector computation. So once you go to the next vector computation, you do a dense calculation on, or you do a maximal with this vector, and to that resultant you add the previous context vector. Now the context vector for the third vector will be the sum of these two, right? So now you perform the dense vector calculation like maximal with this vector, and you add it to the context from the previous two vectors. So this is how it goes on till the last valid character, and after that it just remains the same. So as you can see, wherever this mask is true, you will be doing this computation where you are constantly adding the previous context to the current characters dense vector representation, and wherever this mask is false, you basically just return the previous context. So to better understand, let's just see if I can explain it here. So this was attention, right? So what happens is, let's say you have the same thing here, and your attention mask is true, and false, all the way till false. So what happens here is, you will be doing 0 here, then you will be doing 0 plus 1, then you will be doing 0 plus 1 plus 1 plus 2, and so on up till let's say this is 1, 2, 3, 4, 5. So you will be doing it till 0 plus 1 plus 2 plus 3 plus 4 plus 5, and let's say this is R. Let's assign this value as R, and post this false, you just keep returning R all the way till the last valid till the word length. Now you might be wondering that we had already gotten rid of the padding here, right? Like, why are we reintroducing padding here? Actually, we haven't gotten rid of the padding completely. What we have done is, instead of padding it to 127 length, now we are now the padding length, or the largest word length, depends on the current batch which is being processed, or current shard which is being processed. So if you look at the training file, I'll show you where it is being converted, right? Yeah, here. So now currently I have written this data loader here. You will be able to see this. Yeah, data loader. So here these data loaders are actually passing you the shards which are tagged, right? So it actually has a batch size of 16 and the sequence length of 32, but the words lengths are not padded to 128. They are in their true format and their true length. Now what happens is, when this ragged shard comes to TensorFlow, or comes to the actual training loop, I am converting them to a ragged constant tensor. So when you do this, ragged constant tensor, it's implemented in such a way that it will take the it will pad all the words, or pad all the tensors which are on the ragged dimension to the length which is the longest in that particular batch, or in that particular tensor. So let's say you have a tensor where the batch is 16 and the number of words is 33, but you have the word length as 3, 5, 7, 10, 4, 9, and so on. So here the largest word length is 10. So all the words will be padded to the length 10 instead of being padded to length 128. So here though padding is there, but it is not as significant as 128. So let's say you have the word length as 3, but you have 125 padding tokens. That does not really make sense, and it actually ruins the context as well. And masking is longer than usual, right? You will just keep on doing this where, and you'll just keep on returning the same tensor again and again all the way till, or for 125 times. That is actually very inefficient. So what happens here is, in this training loop, we take that shard and we pad it only to the longest word available in that shard itself. So here in the example it is 10, and you will be returning the same vector for 7 times if the word length is 3. So this is the recurrent step, and I think I did a mistake while explaining that this initial context is taken like this function is done on the initial context first. I think that is not the case. This initial context is this context pref, which is the first context which is sent to this recurrent step, and after that this uh, these tensors are also sent, and it actually happens like 0 1 at one shot, then 1 2, then 2 3, then 3 4. It happens like that, and this function is not applied independently on this initial context. Initial context and the tensor representation, or the first tensor, is actually taken together, like 0 and 1 are taken together, then 1 2, then 2 3, then 3 4 happens all the way like that. And this character RNN is actually constructed in such a way that you can get the final context vector as well as the whole vector representation depending on this return sequence Boolean variable. So if this return sequence Boolean variable is true, you return the whole tensor representation where this recurrent steps output is actually presented one vector at a time in that tensor. But if return sequence is false, you return the final vector, which is this context next at the very last iteration of this function, right? So now this actually can be implemented using a while loop as well. But with a while loop, with a Python while loop, the GPU implementation is not up to the mark. So as I mentioned, Gemini's TensorFlow knowledge was really helpful here, and that it suggested the usage of this tf.scan function with the signature, and it actually helps in increasing the utilization of GPU as well. So let's get back to the blog and continue our journey from there. So this character RNN is what I explained you just now. So as I mentioned, the attention based class, the encoder class is, I replace the attention layer in that and replace that with character RNN. So here if you see that input goes to this transformer encoder which has character RNN and a feed forward neural network, that the output that it generates goes to the word backbone or the global transformer decoder, and the output from this is given to the transformer decoder, which also has a character RNN, but it has a context decoder attention. So now what is context decoder attention? Let me open character decoder for you. So this is character decoder. Now this has character RNNs here, which is the first attention layer which you see in the actual transformer architecture, right? This masked multi-head attention. So in place of that we have character RNNs. Then we have added all of this, right? I still have this multi-head attention layer as it is, and I'm using the actual true attention implementation, which is a cross attention variant. Now why cross attention variant? Because you need to condition this vector based on the previous characters which are encountered, like you have to predict the next character based on the current context and the previous previously appeared characters in the text, right? So you cannot train the model to generate text out of the fly. It needs some conditioning based on the previous inputs or the previous input characters, the current word representation which serves as the context. So when you mix these two together, that is when the model will be having all the information and it will be able to generate the next character, right? So that is how it is implemented. So you can see that it is taking X, which are the previous characters which is generated. So if you see here, this has batch size cross number of words, then n-1 characters and their embedding name, and context is of size, batch size, num words, and embedding name. So and cross attention will happen between this X and this context, and it will generate the next n-1 characters on which it is auto-regressively trained. So that is how the architecture looks. So this is the final architecture. So now we have everything available with us, right? We developed the data set to be compatible with our architecture. We have the architecture with all its nuances and minor details on how to handle variable length inputs, variable length words, and to generate. Now we need a compute platform where we can actually train this model, right? So now, as I already explained before, I am using this Keras fixed precision set global policy with mixed bpro16, where computation happens in bpro16 but storage happens in fp32. So with all of these enabled, my model was around 2 MB, and if I remember correctly, the number of parameters was not really that large. what you expect in the current LLMs, right? So I tried to train it on my laptop, but on my laptop, one iteration on one batch was actually taking 31 minutes, around half an hour. So if you look at so many batches of words and you multiply this with 30 minutes, it is a really long time. So what I did was I was looking at many hyperscalers or cloud platforms available and to get one instance for my setup and train my model. So I finally went with GCP. And if you are new to GCP, this is a wonderful video whose link is available in the blog, and I'll also put it in the YouTube video description. So this video is actually explains you step by step on how to create instance on GCP and how to kind of uh, modify the requirement, modify the components of that instance based on your requirement. So this is a wonderful video. You can refer this to get started with GCP. So I started with this video on GCP, and I created an instance with this configuration. I had four virtual CPUs and a 15 GB RAM and an NVIDIA T4 GPU. This was actually the cheapest available configuration for my practical use case, and I started with this. Now, GCP, whenever you log in with a new credit card and a new email ID, right, it gives you $300 worth credits for free. So this is actually very generous of GCP, and I'm actually very grateful and thankful to them because I did all of my architectural explorations, and the architecture has evolved to this stage only because of these $300 and basically the free compute. So this was at the start of the project, but by the time I reached the final architecture and all of my designs were ready, I was left with only $10 or less, and this was not really uh, enough for the training, right? So I had to spend $300 more from my pocket to actually train this model end to end and achieve the stats which I'll show here. So these are the stats. So as you can see, this is the sparse categorical entropy loss, and it started around 1.1 on the higher edge of 1.1, and it decreased and reached up till 0.7 on the higher end of 0.7. And this red line which you see is actually one complete epoch over the entire training data set. And this is the validation loss. So I had around 2,150 batches for training, and after every 430 batches, I used to run validation for 110 batches or 110 steps, where it was a forward pass over 16 16 batch size, and even that you can see is kind of it started on a high level here, and it decreased and it is kind of going haywire, but the overall general trend is that it is decreasing. So here also this red line means the completion of one whole epoch over the whole data set, right? Now I also generated new tokens with the model using a generate function which I have written. I'll show you that as well in the code. And where I passed certain text to the model to see what it generates, right? So let's have a look at the generate function now. So generate function actually comes only for the decoder and the word backbone, right? Character encoder, the whole work of character encoder is to only look at the data, encode it in a compressed format, and pass that compressed format to the word backbone. So now word backbone is here. Now word backbone has a generate function because it is doing the actual heavy lifting of the sequence modeling or the language modeling, right? So it is accepting certain inputs, certain vectors which represent words here. In other LLMs where they use byte pair encoding, it represents the context vector or the vector representation of a token. In the BLT, the byte latent transformer, or the space byte or the megabyte paper, this vector actually represents the compressed representation of a patch, which is a collection of tokens. So word backbone actually does that example which I told you, right? The cat sat on the, so that mat word prediction is actually done by this model, this word backbone. So this has to have a generate a function where it accepts certain context and it produces more number of words, which is based on this, like match new tokens, right? So basically how this works is, let's say you have this context, right? You have, let's actually work here. So let's say you have 1, 2, 3, 4, and 5 words, and you want to generate 5 new words or tokens. So character encoder kind of encodes all of these and creates richer representation of all these 5 words. Then what this generate function does is it accepts these inputs. So these are actually the inputs. Now what happens with this for loop is you generate the first word right now. So let's go here. So you generate 1, 2, 3, 4, 5, then you generate 6, right? Now after 6 it will concatenate this 6 with the previous 5, and it will create a new tensor for inputs, and this input again goes into the model where it looks at all of these 6 uh, input tokens for its context development, and then it predicts the next uh, next token or next word based on based on the first 6 words or first 6 tokens. So this loop happens all the way till you have generated how many yeah, so let's say you have 5, right? So you have generated 1, 2, 3, 4, 5, so one last iteration, which is this. So this is where you start, and this is what is called uh, so this is what is called auto regressive generation. So you are taking the whole context first, then you are computing what is most probably going to appear as the next word or the next token. Then you generate it, then you concatenate it with the original input, then you again pass on that to the model to predict the next word. So now here you can see something as max attendable words, right? So this is what is called as the attention span. You can't have infinite number of words in an attention span, or what you call the context window or the attention window. So you'll have to cut down at some part. So you kind of forget the extreme tokens which were given to you at the start, and you only focus on the central part of your input or the central part of your context. So let's say here the attention uh, span was, let's say, 3. Not we can say, let's say 5, right? Let's say the attention span was 5 itself. So at the start you can consume all the 5 tokens and you can generate the 6 token. But when you want to generate the 7 token, you can only attend to 5 tokens. So you'll have to give up on this one and you'll have to start attending from 2. So you attend 2, 3, 4, 5, 6, and you generate the 7th one. By the time you reach to the 7th one, you'll have to throw out the first 2 tokens, because you can only attend to 5 tokens. So you have to start from 3. So this is how the attention window works, and this is a simple way of achieving it. So you basically take the window length from the back and you attend only to those words, right? So this is the attention sorry, this is the generate function for the word backbone. Now going back to the character decoder, right? Now character decoder also has to generate characters, not words or not tokens. It has to generate characters based on the context which it gets, and it has to generate those characters auto-regressively, right? Now what I am doing here, now if you actually remember or if you have read the byte latent token paper, what they say is you can actually run this character decoder parallelly, right? So let's say you generated 5 words here, right? 5 patch representations. You can run the character decoder from here, right? From here all the way till here parallelly. So you can have 5 instances of character decoder running on each and every word representation or patch representation independently, and they can generate the characters the characters for you parallelly. So it will generate all the characters which are supposed to be present in this patch uh, uh, with its independent instance of character decoder. So for the 7th word or 7th patch, so for the 8th token or the 8th patch or the 8th word. So now I am not generating the characters in this way, because I think you have to give the newly generated word, which the decoder generates character by character. The character decoder generates character by character. This word has to be passed to the word backbone, so that it can condition its context in a better way. I'll explain you this concept in with an example. So let's say uh, you have I'll be writing this in English because writing it in Devanagari is a little difficult with the current keyboard. So you might be aware with the person called as Arjuna is the archer who's the most capable archer from the historical event of Mahabharata. So he is the son of Kunti. So he is Arjuna's mother is Kunti. So Arjuna is also known as Kunti Putra. So Kunti is her name and Putra means son, right? But there is one more representation is Arjuna is also known as Kaunteya. Kaunteya means Sanskrit has one more concept where you can generate words from a root word. So Kunti's son is called as Kaunteya. So now let's say you are given some context and the character decoder predicted K. K. But the next prediction can be A or U, right? So if you produce Kunti Putra, the words following it might actually differ. And if you produce Kaunteya, the words following it might actually differ. So instead of generating these characters parallelly, what I thought is I would generate these words one by one instead of having multiple instances of character decoder and to generate parallelly. So this is why my character decoder is a lot comprehensive and a lot bigger when you consider a single like token by token generation or a word by word generation. So what I'm doing here is I am accepting the context which is coming from the word backbone. I'm accepting the embedding layer which serves the purpose of mapping the characters to a vocabulary, and there are the character RNNs as well. So what I'm doing here, I'm getting the word embedding, then I am passing these I'm passing this character embeddings to self. So self is basically this character decoder's call, and I'm passing the character embeddings, and I am passing the context, I'm passing the word mask, and I'm passing the character RNNs. So after all of these, it generates the next character conditioned on the previous characters and on the context. So after this, I'm doing a matmul with the embedding layer. Basically, the older GPT models has have this concept, right? So whatever matrix you use for embedding, you can basically multiply the model's output with the transpose of this matrix to map it to the vocabulary size or the number of characters available in the vocabulary, and then do a softmax on that. So you get the probability of the most probable character from that softmax layer. So I am doing a categorical random categorical. So basically, this is how this works is it basically takes the vector representation, and you don't have to explicitly do a softmax here. This categorical actually does it for you, and it spits out the character which has the highest probability of appearing after given number of characters and the context. So then I cast it to an integer. Then you can actually do what you say. You can concatenate it with the current. You can concatenate it with the previous appearing characters, and you can also update the mask. So let's say you get the end of the word character, right? So after getting that character, you basically ignore all the next generated characters. So basically, that is how this mask is being updated. And after that, you kind of this is where the padding occurs, right? So since in this data set the maximum length word is 125, I'm keeping that data point for the generate functionality as it is, because the model has seen 125 length words, so there is a chance that the model can generate a 125 length word. Beyond it, the probability kind of dips because it has not seen those words of that length. So I am keeping that data point still. I am considering that data point for the generation of words at least, right? So that is done. Now let's actually look at the model. Now in the model, what happens? So model is basically the whole representation of character or the encapsulated representation of the character encoder, word backbone, and the character decoder. So this is how it is initialized. So there is embedding layer, then there are certain character RNNs, then there is character encoder, word backbone, character decoder, and the final logics, which is still in float 32 to maintain accuracy and numerical stability. So you first call character encoder here, then you pass these words to the word backbone. I think this is the word backbone, and after that you pass it to the character decoder. So after you do that, you get the final logics on which you train. When you come to generate function, you get the actual words, you pass them through the character encoder, you pass them through the word backbone, you get the last word here from the character backbone, you pass this word to the character decoder's generate function, and based on this context, the input is conditioned and it generates the words, and those words are concatenated back to the original words. This is where I mentioned I'm not generating the characters for all the generated tokens parallelly, right? In the for loop, there is only one character decoder's instance, and that character decoder is used to generate one word character by character, one at a time. So here I'm again concatenating it to inputs, and the input mask is updated in the same way. And this for loop kind of continues till all the till the required number of maximum tokens are generated. Now let's get back to the block. So this is how the loss functions look, right? So now we have achieved whatever we wanted to achieve, but did this model work? Let's look at a retrospective. Uh, my target was to beat GPT-4 Llama and Gemini, very far-fetched goal, but did I actually do that? No, I could not achieve what I intended to achieve. Kind of a bad ending to whatever all this effort, but this was actually a kind of byproduct which I wanted to achieve. That my model actually learns the Sanskrit language nicely and can actually beat these models, but it was a far-fetched goal and I could not achieve it. I'm of course sad about it, but it's not disappointing really, right? Because as I mentioned before, I was running a generation after every 430 steps, right? After training every 430 batches. So this is how it generated. So this is the input text, and this is its generation. As you can see, this doesn't really make sense when you kind of generate the when you kind of generate it the first shot. Then after the second validation, this is what it generated. So it is kind of getting the style. So here it generated like almost close to let's say 60 characters per word. But here it understood that no, not all words need to be long. Some words can be short as well. So here it understood the word length. Then I think here it was trying to generate words which were short but which are also meaningful, and it was trying to apply the concepts of what you say, the Sandhi and Vibhakti. So you can see some null characters here also, right? So that is possible. I'm just guessing that it was trying to do that. Then it kind of overdid that in this generation because you can see many null characters here. Then by the time it reached the end of the data set, it tried to make sense of whatever data it was looking at. It tried to generate some sensible text, but here also it kind of failed. But here, what I think it is right, here it has gotten the style up to a very nice extent, but of course the text does not make sense. Then this was like after 1.2 times the data set, like one whole data set and 20% of the next epoch of the data set, right? So here is where it generated this kind of text. So this is gibberish. This is of course gibberish. It is not coherent. But the architecture kind of works because the loss is decreasing, right? Maybe the model is not large enough so that it can learn everything properly, and it can express its thoughts in actual coherent and coherent text that makes sense, right? So I think this project is not, I'm not concluding this project here. I'll still be working on the version 2 of this project. But this project isn't about beating any benchmarks or beating any model, right? Because I don't have the compute that these large models are trained on. So I will try to code up the next version of this model and try to push that code in GitHub, and I will probably be back with a next blog and next set of videos to explain what I've done in that architecture. So, but again, repeating again, this is not to beat any model or not beating any benchmarks. It is just to find out, exploring and finding out that architecture actually matters. We cannot always have more data and a larger model, but still use a fundamental algorithms of which is basically dependent on statistics, right? Byte pair encoding is actually statistical algorithm where it sees where it groups the chunks which it sees more often. but making the model actually understand the language might require some changes in our fundamental algorithms itself, which come before the actual model computation, right? So that was the goal, and I think we have achieved that with all of this exploration. So what will be the future steps? As I mentioned, I'll be coding up the next version to support more languages, and we'll be back with a new blog and new set of videos. Parallelly, I'll also be looking at certain shortcomings. I think this model is not really complete at its current setup. In the current state, there should be some shortcomings in the model. There should be some nuances that I've missed, some details that should have been addressed I've missed. So if you are going through this blog and you're going through this video and you are also going through the code base on GitHub, if you find certain details or certain implementations are not right or it can be improved, you can drop a comment on this Medium blog or on the YouTube video, or anyway, you can also contact me on LinkedIn. I have given my LinkedIn profile here. You can message me on LinkedIn as well. So I'll try to address whatever comments you post on any of these platforms and see if I can enhance the understanding of these models, or enhance the model's understanding of the language or multiple other languages. So I'm also planning to do one more retrospective from my side itself on mixing and matching concepts from the previous commits and the current setup. So I never did a regression with character RNN actually during this journey, right? So I would also like to see how that works out. So character RNN, but instead of token classification, it will be a vector regression problem. So that is how it is. So I'll probably be saving some more money over some more months for getting the compute on GCP again, and training the model with the next version. So you can have a look at this blog. I'll be making this public soon, and if you like this project, you can contact me on LinkedIn here, and you can check out my other repositories on GitHub. So thank you everyone for watching, and meet you in the next one.